everyone. I'm going to pass it over to Milos to introduce Krešimir, because I've only met him once or twice, and I'll try and switch off the transcript, or maybe that's not possible. I'll switch it off on my. So yeah, over to you, Milos, and then the rest of you switch off the cameras and microphones to keep the bandwidth going, I guess.
Yeah. Thanks, Rob. So I'll just very quickly introduce Krešimir. So Krešimir Begović. He's a researcher, comes from Croatia, Zagreb, if I'm not mistaken, but feel free to correct me. Might be somewhere nearby. So I first met Krešimir at the Czech University of Life Sciences in Prague several years ago when he was doing his master's thesis or master's work. And then actually not long after that, he started his PhD at the same university. And basically over the past few years, we've kind of had this unofficial PhD student supervisor relationship, kind of. And so we've worked together on several publications. And also then about 3 years ago, he started working with me as a technician on our Replicate research project. So there we've been sort of focusing on developing multi-parameter Turing temperature reconstructions for Central and Eastern Europe, and also developing some new methodological approaches for new types of, developing new types of Turing parameters and using them to extract climate information. So he's done an excellent job, and he's been a really big help with data production, and then also with helping to develop and implement some of the new lab techniques. And recently, a few months ago, he's successfully defended his PhD work. And now we're kind of continuing, on to finish off some ongoing work, and also he's involved in helping or sort of exploring some new potential research project ideas. So I think with that, I can hand over to Krešimir, and feel free to add anything or if I've left something important out. But yeah, looking forward to the talk. So thanks.
Yeah, we didn't check it. Hopefully you can share your screen. I assume you know what you're doing.
We can try that out immediately. Let's go to Windows. Let's go to PowerPoint. And it should be shared.
Yep, we can see your screen. It's not in presentation mode yet, but we can see your monitor.
Yeah, cool. Awesome. There we go. We can enter presentation modes. All good?
Yep, all good.
All right.
Okay, enjoy.
Thank you. Thanks both Rob and Milos for the introduction. Yeah, basically Milos covered more or less everything. When put into perspective like that, it's quite a long time since first time we met, and then how we continued the work, and hopefully we'll continue in the future with some new topics and new ideas. And maybe one of, I wouldn't say a novel idea or a novel topic, was part of this study, which was part of a cooperation with Charles University colleagues, Honza Tomajer and Václav Treml. And the topic was involved around exploring the spatiotemporal changes in drought sensitivity of Norway spruce and Scots pine, but through the utilization of multiple Turing parameters, in this context, ring width and blue intensity, but also exploring a multi-method approach to, in a way, dissecting and disentangling drought effects on tree growth and, in a way, wood density through the wood density surrogate. So this presentation was actually part of the Trace 2023 a couple of weeks ago as a poster. I think I saw some of you who were there and who have seen and might have seen the voluminous poster that was exhibited there, but others who haven't will actually have the chance essentially today, because the presentation itself will, in a nutshell, follow the outlines of the poster. I'll give a brief background, some knowledge gaps, knowledge aims, methods and aims, research area, and then show some results and conclusions. But I'll also intertwine some of our findings from this study with the study from 2020, which was my first publication and my first exploration and playing around with blue intensity, just in a different area. But we'll come to that in a moment. So, as a background, what better way to start than with a typical, let's say, pointy end of the hockey stick and the predictions, the climate predictions. Essentially, over the 20th century, especially in the last 70, 80 years, there's been intensification of global warming, visible through the exponential increase in greenhouse gas emissions, rising air temperatures, but also shifting hydroclimatic patterns, and maybe more importantly for forest managers and generally policymakers in let's say in conservation and forest management, the intensification of natural disturbances, which are predominantly regionally dependent on what type of or extent of these disturbances will have on forest ecosystems. Now, these disturbances and these changes, why is it important to be able to not only identify them but to predict them? Is because of their impact. Now they have the limited capacity of forest ecosystems for in carbon uptake, which is seen through either biomechanical constraints to tree growth, offsetting carbon cycle feedbacks, but also through demographic shift in tree species. And many of the models in the last 10 years have kind of shown that the projected changes, if the patterns of climate factors continue in a way they have been seen in the last century, they will lead not only to demographic shifts, but also could lead to reduced productivity and faster turnover through shorter carbon residence time, or through these widespread mortality events that have been actually seen in certain parts of Europe in the last couple of decades. However, the particular interest of this topic or of this study was the increasing occurrence of extreme climatic events, particularly the combination or in tandem heat waves or high temperatures with very low precipitation or generally moisture availability, which was termed hotter droughts, and can have a very explicit impact seen through the figure through in Šumava, where in just a range of 2 years we can see in the same or around the same time completely different ecosystems in a way, predominantly caused by a strong defoliation caused by very hot late summer. Now, in order to understand drought effect, just a small background, the easiest way to do it is through the hydraulic framework, which essentially hypothesizes 3 kind of possible directions of tree mortality from drought stress. So one is through carbon starvation. So the longer the water stress, the more carbohydrates, carbon will be spent by the tree, carbon storage. And if the duration of the water stress is so long that it actually subdues the effect of photosynthesis, it can actually lead to death. Another pattern or pathway is the intensity of water stress. So if it's a very high intensity, it can actually lead to desiccation, embolism, and that way leads to some type of mortality. And then the third one is either a combination or amplifying of both, plus adding the impact of biotic agents. But what we see and how we identify drought events and how we can actually see them in tree rings is to reduce annual growth. So these typical very narrow rings. But in recent decades, it has been more prominent to investigate the effects of recurrent drought events, so compound drought events on tree growth, because they were seen to leave so-called drought legacy effects, which are essentially lags in tree growth recovery, which can persist for several years. And a couple of studies from Anderegg in 2015 and 20 have actually played around with different effects of these droughts on a large scale, and have shown that subsequent droughts have a much higher impact, anomalous impact on tree growth, but also that the drought effect or the drought legacy effect is very tied with sites, so aridity of sites, but also is conifers in particular exhibit a heightened sensitivity to recurrent droughts. This is mostly, it could be explained through biological specificities of conifers, but also site quality, where conifers are growing, and others. But essentially, a multi-parameter tree ring assessment of drought legacy effects is in the area of Central Europe in a way somewhat lacking. So that's one point. Another point, generally climate growth relationships, or how we quantify the impacts of climate on growth, is through usually have been used the linear climate growth relationships, and they have shown for a Central Europe where they have quite nicely developed, have shown that the climate response is strongly latitudinally, altitudinally dependent, right? So high elevation, high latitudes, it's a temperature limited growth. When we get to the middle altitudes, we're talking about kind of a mixed climatic signal, and then at low altitudes, it's mostly or predominantly moisture limited growth. However, in recent decades, it has been shown that that these linear functions are not really or not always capable of showing the reality, ecological reality, because the relationship with climate are non-linear. They lead to divergence or non-stationarity, and this can depend on environmental conditions. It's variable. It varies through species, but also model type. So again, using a multi-parameter approach of assessing the climate associations from European unmanaged forests, particularly, is also something that is somewhat lacking, not in that extent. And kind of in a short, what is the general outlines or gaps, let's say, that the paper tackles? It's to reduce the uncertainties regarding intra and interspecies variability in these drought legacy effects, not only in ring width, but also in wood density. Also to investigate the long-term impacts of hotter droughts, of these tandem occurrences of weather and climatic extremes, on the general climatic sensitivity of Norway spruce and Scottish pine across a relatively broad environmental gradient. And the last one is to explore the utility of wood density surrogates, in this case blue intensity, for assessing tree hydraulic properties, particularly in drought-prone environments, but also in some temperature-limited environments. So in a nutshell, how we want to examine the common growth trends and growth climate associations using ring width and blue intensity, disentangle the proportional effects or the proportion of growth which is modulated by temperature and moisture since the 1940s, and to identify these drought legacy effects in growth patterns in both ring width and wood density during and of course following severe drought events. Now, just to give a background on the research area, the study was focused mainly on Central Europe, concretely Czech and Slovakian area, covering several mountain ranges like the Sudet Mountains, Ore Mountains, from our region, but also towards the east, basically the Western Carpathians, the Tatra Mountains. The actual sites were distributed. We can say that we had a relatively good latitudinal and altitudinal gradient. Here shown are depicted with different shapes. Our low elevation sites, different colors show different species. The blue letters indicate where the blue intensity or blue data was available. So in a nutshell, we can see that we covered a relatively good environmental gradient, broad environmental gradient of both spruce and Scots pine natural distribution in Central Europe, but also a climatic gradient going from very high elevation, cold and wet spruce sites and pine sites to warmer and drier combination of pine and spruce sites. Now, methodologically, I'll not stay too long on this section. Essentially, one of the first things I want to do is to use a PCA with hierarchical clustering, some type of a multivariate analysis that I can kind of validate this categorization of sites based on common growth patterns for this period, 1940 to 2020, essentially. And just by separating kind of sites, grouping sites based on these different matrices and principles, just by a first glance, we can see that the high elevation spruce sites are particularly kind of separate from the remaining sites, which already by itself can be an indicator of specific growth patterns seen or difference between these between the high elevation spruce sites and the remaining sites. But also the next step was to conduct a climate growth response analysis using the regular Pearson's correlation coefficients, not only a static but also a dynamic correlation. So using also a moving window correlations over the same period to also see what the climate signal stability is over the period of interest. Second point was, all right, so since we're predicting or expecting that there will be some or a lot of nonlinearity in our data sets, we want to use the VS Lite for modeling. Now, it is different from the full model, which is shown here on the right, adapted from a recent publication of Honza Tumar. Essentially, not to spend too much time on describing it, but essentially it is capable of predicting or simulating growth, essentially based on 3 inputs: on latitude, which is used for calculation of insolation, and then on temperature and moisture parameters, which are then used in RAM functions to combine to simulate growth and to, in a way, dissect which part of the growth is moisture limited or moisture driven, which part is temperature limited or temperature driven, and combination of both, or where the growth is at its optimal and not actually limited by either. And the third approach, or the third aspect, was to identify severe drought years, and this was done through a combination of using several indices, concretely the SPI and the PDSI moisture indices, and but also through using recently published literature in the last 15-20 years covering the region of interest, and to kind of identify which years were the most prominent or the most dry or the most anomalous when it comes to moisture availability, and to use those years in a superposed epoch analysis. So this non-parametric test, which is very handy in actually quantifying behavior of not only ring width, but also can be used for blue intensity to actually quantify the scope or extent of reductions or changes in these specific extreme years, but also pre and post, depending on the window of interest, which is used in the actual parameterization of the analysis. So just a general outlook of it's gonna be a mouthful, this the results section, but please bear with me. So just as kind of to show the some metrics of the actual ring width, early wood blue and delta blue. Just to, before I continue, I would just want to say that the preparation, the processing was done more or less in the usual way. The standardization was done using a 30-year spline. Both the residual and standard chronologies were developed, but I only will show the results for the residuals here. I used only delta blue and early wood blue, not late wood blue, because the late wood blue intensity, first of all, the results were quite similar to delta blue, and on the other hand, some of the sites did not really go through the pre-treatment, the acetone extraction of resin. So just to kind of minimize any possible biases in that aspect, I opted for delta blue. From these parametrics, just to show that the EPS value, this is for the period 1940 to 2020. Unfortunately, I couldn't go earlier because the early wood blue, for especially for low elevation pines, it basically fell under 0.80 threshold. But in general, we have a very strong common signal in the ring width, an order of magnitude lower in early wood blue and slightly lower in delta blue intensity, with low elevation spruce and pine kind of having the lowest common signal strength. Now, when it comes to actual climate response analysis, this was done per site for individual sites, but here I'm showing only specific seasonal windows, which were the most significant for each category of sites, right? So here I would emphasize 3 findings: the predominant high elevation spruce signal, or is the temperature signal, right? The summer temperature signal, but also a slightly weaker but also significant late spring, early summer moisture availability. When it comes to pines, both low and high elevation, we see as more or less expected, a strong summer, somewhat strong summer signal SP for moisture, but a negative correlation with previous year mid to late summer temperatures. And when it comes to low elevation spruce, here we have a very interesting situation where we have a very broad, as you can see, this very large violins, which are essentially forced me to kind of see what's happening here and why do we have such broad extent from very significant negative to very significant positive relationships with both SPI and temperature. So essentially, I separated the low elevation sites into mesic and xeric sites based on site quality data that I have, but also based on elevation. So we see here exact opposite relationships where mesic sites have a positive relationship with temperature, negative with SPI, and in the xeric sites, this relationship is reversed. Now, when we go to the early wood blue and late wood blue and delta blue intensity results, more or less the results are the same, just that I would emphasize here that with early wood blue, we managed to get a broader signal in pine, both low and high elevation. So we have the whole growing season being the strongest correlation with growth for both SPI and temperature. And for delta blue, the signal was much stronger for high elevation spruce forests. The temperature signal, summer temperature signal, but also we have here a negative correlation, significant negative correlation with summer moisture indices. Again, the separation between in low elevation spruce forests between mesic and xeric sites showed more or less similar relationships, like with ring width, just a slightly stronger signal. Bear in mind that this is not all sites included in blue intensity. We did not manage to develop all sites in time, so I'm pretty sure that these signals will be even stronger and broader if we incorporated all the sites. Okay, so I wanted to investigate the temporal climate signal stability. So using a 31-year moving window. Now here, just not to get confused, it's all shifted forward by 30 years. And if you check at the sites, this is just an example of the ring width temporal signal, and we can see there's a lot of instability, particularly in low elevation spruce sites. So to make it simplified, I grouped again per parameter, per category, with the most predominant climatic factors, which in our case was the summer temperatures for early wood blue, ring width, and delta blue. And just by a glance, or just by seeing how these lines are distributed, we can see that apart from temperature ring width and delta blue for high elevation spruce forests, which are darker brown color, lighter brown color is low elevation pine spruce, and with the pines it's the same principle, just with green colors. So apart from ring width and delta blue temperature signal in high elevation spruce forests and low elevation ring width a relationship of pines with moisture, the rest of the signal is very, very unstable and very non-linear, kind of bouncing from significance to non-significance over these, let's say, categories of sites. So the VS line modeling output, it made sense to use the VS site model. So the partial modeling growth responses here are shown in a specific way, right? So the red lines are temperature response, partial growth response, the blue lines are the moisture, and the black dash line is the integral growth rates, again, per category of sites. Now here, there's a small difference is that the darker colors represent the recent 20-year period, while the lighter colors represent the oldest 20-year period, so 1940 to 1959. And what we can generally see is that with temperature, the growth responses have increased towards recent times. We can see that even the season has somewhat extended across all sites, and particularly we see this happening in the earlier part of the season, where this autumn part is more or less relatively stable. While with the moisture, kind of these duodecadal patterns, we don't really see any trends, any increases or decreases, but generally we do see an increase in moisture sensitivity simply by the extension of this temperature moisture overlap, right? However, I wanted to also kind of go even deeper and see what is the annual contribution of each of the dominant climatic factors, so temperature, moisture, a mix of both, and then a non-climatic, let's say, or an optimal climatic influence on growth over the whole period at first. And essentially what we can see here ties very well with linear relationships, which shows that the almost 45% of growth is limited of spruce growth is limited by temperature. In low elevation, there's also a very strong mixed signal, while in high elevation, we don't see really a very strong mixed climatic signal. While in pines, we have a very high moisture sensitivity or moisture limited growth in low elevation forests. But interestingly, in high elevation pine forests, we have almost a 50% of kind of climatic optima. Now, when we go into the interannual relationships here, I did not yet include linear trends, but essentially all the linear trends are showing something very similar that we've seen in other studies from the region, which is a kind of a slow increase of moisture limitation of growth, or a mixed climatic signal, and a slow reduction of temperature limited growth. Now, when we actually see how the actual predictions or the model growth looks like, here it is. Essentially, the red line shows the predicted or the model growth by VS Light model. The black lines are the ring width indices actually observed. And in the right corners, you can see the calibration versus verification correlation. The calibration was the 1940 to 1980, 1980 to 2020 was the verification period. So essentially for spruce, it is doing a very good job when it comes to the overall correlations, albeit at certain periods or certain points, it is kind of underestimating or overestimating certain high frequency and mid frequency trends. But with pine, it kind of suffered, particularly with high elevation pines, where we have a very, very low correlation, almost no correlation, 0.66 in high elevation pines, while in low elevation pines, this is much better at 0.358, the verification period, which kind of indicates there is some limitations to actual VS Light model when it comes to predictions, especially from sites which have this mixed climatic signal, which we have seen in high elevation pine forests. And last but not least, the superposed epoch analyses was done separately for each of the parameters, and again for each of the category. The colors of the categories are the same as with the previous figures. The brown ones are the spruces, the green are the pines. And here I opted to for only 3 years pre-event and post-event. Why? Because many of drought events or these severe drought events, particularly in recent times, overlap. There's a situation where you have and for instance, from 1990 to 1993, there is essentially all 3 years are super dry years. So many of these years had to be excluded. So I only kept the years that were actually not overlapping, in order to minimize any kind of biases or weird behaviors. And then also the red and blue area are essentially mean regional temperature red and blue moisture for these event periods, right? Just kind of for a visualization. But essentially what we can see is in ring width, we have a very strong decline of or a significant response of both low elevation spruce and pine in drought event years. But also we can see here not really visible. If I extended the pre-event a little bit further down, we can see that the high elevation spruce reacted very strongly to anomalously low temperatures. And this is also corroborated in Delta Blue if we pay attention to that one. But in Delta Blue, we have a situation where we have a low elevation pines exhibiting a post-drought kind of response, a year after the drought event, showing some type of response. Now, when we talk about the early wood blue, here it's the strongest response was only seen with pines and not necessarily with spruces. Although again, we have a kind of in a set 2 years after the drought event, there's something happening with both high elevation pine and spruce. Technically, it should not be climate related. It should not be a drought because all the kind of droughts that were overlapping were excluded, but there could be still some type of anomaly. And the figure on the right, which is essentially a superposed epoch analysis, but of temperature and moisture, but done for specific regions. I just wanted to see kind of if there is a specific difference between different regions when we kind of average the climatic conditions, because in the actual superposed epoch analysis shown on the left, it's only the regional data is shown, right? So I just want to see if there's any kind of differences climatically between these three regions quite coarsely, but essentially what we can see here is no really significant big differences between each of the regions. Now, how does that translate into actual growth patterns and growth trends, which is, I guess, maybe the most interesting and most important? And well, this is how it looks like. Now, this is shown only for the 20th century. The wiggly line is essentially just the local weighted regression, just fitted essentially for visualization, not for parameterization. And essentially what we can see here is a relationship that we've seen also in other high mountain forests, particularly towards the east and north, which is an increase in high elevation spruce forests in the recent decades. But also we can see a strong decrease in low elevation spruce forests. This is also mimicked by pine forests, high and low elevation, but even by visual viewing, we can see that this dip or growth decline is much weaker or lesser in pines than in low elevation spruce. Now, we had one kind of, I wanted to do another comparison, which is from two sites where we have Norway spruce and Scots pine growing literally at the same site. So from the data that was available, I only had the Rapstein, which is the most western site of our site categories, let's say, of our research area, and then the most eastern, essentially, which is the Slovenské raj, where we have both species growing in tandem or very, very close to each other. And essentially, here I wanted to see what is the basal area increment trends between the two species. Now, the red ones are the spruces, the blue are the pines, and essentially what we can see here is that from the 1940s to 2020s, spruces have generally a larger growth, or they increment basally more, but also they have a stronger dip compared to the pines, particularly in this recent decades. The same situation is in the west and in the east, which indicates to me that this is definitely species specific and not site or regionally specific. Now, this is very similar to the results we had in our study from the Dinaric Mountains from Croatia, where we compared mixed species primary forests. We focused only on the conifers, and we used the early wood blue intensity and ring width. We also used the late wood blue intensity, but it wasn't so significant. But the early wood blue intensity and ring width show something very similar that we see now in low elevation spruce forests. First of all, there was a climatic instability. So on the figure on the right, the blue window is early wood blue intensity for Abies alba on the upper part, and the lower part is the Norway spruce. And what we can see here, the red is the relationship with temperature, the blue is the relationship with precipitation, summer precipitation, summer temperature. We see with ring width, there is a very strong non-linearity in relationship from significant to non-significant, albeit growing, increasing in recent decades in silver fir. But in early wood blue intensity, we see an improvement in climatic signal or climatic stability compared to the ring width. Second thing, what we found in that study was when we did the pointer year analyses, just by a combination of pointer year analyses, we saw that the spruces exhibited much more pointers compared to the which is shown in the A and B figures compared to the silver fir. Early wood blue did not catch did not have so many pointers, but interestingly, spruce did ring width wise. And also what we found is that there was a clear evidence of a physiological weakening on Norway spruce trees, especially declining since, let's say, 1970s, 1980s, while the fir is not exhibiting those type of relationships, which is quite interesting because many of the recent studies, and some of them we actually heard even a trace from the, I think, Pyrenees and other areas where silver fir is strongly declining. Now here, obviously, these are very different, compositionally different forests. Here we're talking about mixed species primary forests. But still, what is interesting is this growth decline in Norway spruce, which could indicate that there will definitely be some type of distributional shifts, compositional shifts and distributional shifts when it comes to spruce. And kind of just to sum it up, the general conclusions, our linear growth climate analyses corroborated by the partial growth responses from the VS Light model showed that the shift in climatic constraints increase growth in temperature-driven mountainous Norway spruce forests, but they also lead to growth declines in mixed response Scots pine mountain forests, and also moisture-limited low elevation spruce and pine forests. Second kind of finding would be that the temporal non-stationarity should be used for modeling climate growth relationships in the future. And it also indicates that the future development of conifer forests in Central Europe, especially if these changes become even more extreme, that these relationships with climate and with these conditions will be increasingly modulated by local site and microclimatic conditions, which will be quite harder to predict. So this would require more researches, future researches, retrospective and prospective, on these from various sites and from various kind of parts of natural distribution of particularly of conifers. Another finding is that these discrete drought legacy effects were visible not only in ringwood but also in early wood and late wood blue, and they were most pronounced in the low elevation forests, particularly pine forests, but also in high elevation pine forests. Another conclusion would be that the declining growth trend in Norway spruce, especially the one we've seen in low elevation forests, suggests that the predicted increase and duration of summer droughts, if they continue and if they continue to be recurrent, will likely drive future growth declines, which would then result in increased mortality rates across the Central European region. And finally, I think another addition of this paper, which is currently in preparation and hopefully will be submitted in the upcoming weeks, months, is the advantage or kind of the applicability of blue intensity parameters as proxies for not just short-term drought impacts, but also to be incorporated as part of antecedent and contemporary climatic drivers on wood anatomical features without going into too much details. Albeit our results didn't go really into that much detail, but it does show a prominence of the utility of these parameters for utility in drought-prone environments, not only in Central Europe, where we expect where it's an obvious drought-prone environment, but also in mountainous areas like the Dinaric Mountains, where it was shown that early wood blue not only improves the climatic signal and the broadness of the signal, but also improves the temporal stability, has a higher temporal stability, and thus are very relevant future Turing parameters for researching climate response analysis of various conifers. And I think with that, I will finish. And thank you all for the attention. And that's all from me for now. So thank you.
Thank you very much, Krešimir. Great talk. Any questions, anyone? I've got a few, but I'll let others jump in first if they want. Oh, okay, I have the first question then. You use VS Light, and it really struggled with the high elevation Pinus sylvestris. So I'm not surprised that we've got a mixed signal and it's very hard to get a sort of traditional correlation response with temperature or whatever because of the mixed signal. But I am surprised that VS Light struggles to actually model that, because isn't that the whole point, that VS Light should be able to pick up that kind of mix of signals from one year to the next?
Essentially yes, and it has shown to be very useful for capturing for other species. But with pines, there is something specific, particularly about those sites, because on those sites, pines, the site quality plays here a big role, right? And there is no input for site quality in these models, right? So he only is, especially VS Light model, he's only limited to these three inputs. And with these sites that we had the high elevation pine forests, these sites were very poor quality, right? So if he just takes the altitude and the input climate parameters, according to him, it should be a mixed climate signal or an optimal climate impact on growth, but it's not really the case when it comes to the actual sites. So I think in a much broader study where the VS Light model was combined with the full model and linear response analyses from Honza Tumad from this year, actually, he has shown very, very similar or almost the same relationships where the high elevation pines had the lowest correlations when it comes to these verification calibration periods, but also it showed the highest variability between the actual sites. So some of the sites in these high elevation forests actually do pretty well. It's like above 0.4, but then you have sites that are calibration very good, 0.4, and then the verification period just goes down, just goes to negative correlations. So there is something specific about site quality that is not being captured fully by VS model, and it does suffer with these specific mixed climate signals from sites that are expected to perform better, but simply because of the quality of the actual physiographic site attributes, they're not. And then we're seeing this type of very strange, I mean, 50% of optima climate, non-climate. I mean, it's it was very surprising for me to see that. And yeah, there is a limitation to the model itself. But in general, I mean, if we exclude some of these sites of the high elevation pine forests, it still does a pretty good job when it comes to parameterizing the growth and especially capturing these high frequency trends. So I think that's kind of the advantage of VS Lite model. But the VS model, the full model, would probably do much better, and incorporating that into D-step analysis would. And then I don't think it would show such drastic differences when it comes to model predictability.
Anyone else? Georg, go for it.
Thanks, Krešimir, for the very rich and comprehensive presentation. I have two questions, I guess, related to the drought part that you presented at the end. So one is you showed for some chronologies there was a delayed response. Now my question there is, what is your explanation? I mean, is it the seasonality of drought, or maybe, you know, in certain sites the soils were moist, so even if there was atmospheric drought, that was synchronous across all the sites, but maybe thanks to a larger soil water pool, maybe the drought didn't really stress the trees early enough. So maybe when they were stressed, growth was already done for that year. So that would be an explanation why it could only translate for next year's growth. That was one question. And the other bit related maybe is, well, did you also struggle a bit with drought years that were really close to each other? I mean, I just realized when we use superposed epoch analysis, more and more we run into troubles that actually we miss the reference periods before and after, because even within that, you will have an additional drought year.
I will go with the second one, and yes, there was definitely a struggle, particularly in these recent times since the 1990s, because the occurrence of these drought years, if we use these moisture indices, but also from literature and from just general observation and climatic data, there's more of them, right? The gap between the years is much smaller. So it just prevented me to actually develop it on a much larger, over a larger window. So capturing just the 3 years pre-post managed to exclude some of the droughts, but I also had to exclude drought event years that were overlapping. I couldn't get them in these 3 years. So like I said, the 1990, 1991, 2, 3 were not even there. They're not even included. And yet they are probably the driest, if not including the last 5-10 years, the driest period in the last 100 years, these specific small period. So yes, it was very tricky to capture it and to combine these, but also there is Stefan, I think, did a good paper. I don't know if it's out now or not, but he was mentioning these limitations when it comes to drought legacy effects and how we interpret them, and how much of that is actually autoregression, not just of the climatic data, but of the actual biological memory effect. So there is definitely limitations, particularly, but I still wanted to play around with it, particularly with the blue intensity, because I don't, apart from Emily and Rob, I think from this volcanic eruptions superposed epoch analysis where you use the Latewood blue or Delta blue, I'm not quite certain now, I don't remember which one. I still wanted to kind of play around and see, okay, is there some type of utility for it? And for this ties in with the first question when you asked about this post-drought events, what could possibly happen? And I agree, very. That's one of my explanations would be yes, there is again impact of sites, but also the impact of these droughts. These droughts, where we see this lag, we see it where we see in the high elevation pine forests. Again, much poorer site quality, but also high elevation forests perhaps did not have such a strong drought, right? We did not use droughts particularly for this area, right? This is a regional exploration of climatic data, of moisture indices for the whole region, combined with some literature findings. But essentially, another explanation could be that we did so see in the linear response analysis, but also in nonlinear, that the pines are very dependent on previous year conditions. So if there is a drought, right, in that year, in a specific year, and particularly pines don't necessarily react, or they manage to, because of the seasonality of the drought, they manage to slow down growth, kind of close the stomata. And if the conditions improve later in the autumn, they might still reactivate, let's say, and still grow. But perhaps because of this very short period of the previous year, or particularly that drought year, in the next year, there might be some type of a response, some type of a signal, some type of a reaction where the trees maybe don't have so much carbon, or there might be something non-climatic related, albeit that is now kind of pushing it. Yeah. So it's very hard to find the explanation for this post drought, but this did happen only in pines, in high elevation pines, where we see this 1 year kind of lag, while the rest more or less recovered. But when we go deeper into the actual sites, again, we see a very high variability between the sites. So some sites did have a response, particularly in a drought year, and they did not have a response in the next year, right? They did not have this lag effect, but others did. And something similar, I did not show it. Maybe I have somewhere here available data, but I had similar response for low elevation spruce forests, where I have, very interestingly, I have sites that are spruce sites that are drier. They have a very strong and very obvious response to a drought year. In the event year, they do a response, slowly recover. But the mesic sites did not show a response. They did not show a decline in the year, but did in a year after, or even 2 years after. So there is definitely, I would say, there's this addition of the site just general site attributes, whether it is site quality, whether it is the retention of water, whether it is that's from one perspective. From another perspective, whether it is the seasonality of droughts. I think all of this kind of plays a role, and each site will have a different response. When we group them together like this, it's very hard to see it. But when we see the actual individual sites, then we do see this variability in responses. Some have lags, some have responses in the exact years. So especially with these low elevation, especially with these sites with forests, with trees that are mixed in their climatic response, mixed in which the macroclimatic factor is the dominant for growth in a specific timeline, they will have a higher variability of responses. But again, for me, what I would focus on would be the actual growth trends that we see and the actual basal area increments that we see. And here is where I think these results and these differences, site variability plays a big role, because as I've shown on just these two groups of sites where we have the pines and the spruces are having much larger growth declines compared to the pines. But generally, they also have a much larger basal area increment over this period. So I would say there's no simple response. There's probably a combination of factors, whether it's site, whether it's seasonality of droughts, or whether it's functional traits of the actual species. I can't really say with certainty, based on these results that I showed, that it's one or the other or the third. I would say it's highly likely it's a mix of things, plus added this general site variability. That would be my explanation.
So complexity of ecology. Maybe just a thought there. If I remember, you defined drought by the summer months, right? June, July, August. I have seen that people sometimes use a longer window just to account for soil drought effects. Mm-hmm. Maybe this is something, if you haven't tried yet, to explore, and maybe it adds to what you just mentioned now. Just a thought. Probably you did already.
Mm-hmm. I did the growing season, and it was more or less similar, but the stronger signal was for the actual summer season window over the whole site elevational environmental gradient.
It might be better to use PDSI rather than SPEI, because PDSI will then theoretically have a groundwater estimate, and that might make a difference with regards
that was my thinking as well, but no. SPI was again better, stronger, and kind of showed more. So again, it's kind of okay.
We have the same with Bavarian forest spruce. It was always better with SPEI or precip, and then it was the PDSI that was weirdly not as strong.
But in the Dinaric Mountains with that study from 2020, PDSI was stronger than precipitation, and PDSI showed these very distinct relationships, or this kind of a very strong response in early wood blue intensity. It was very, very interesting to see here. But so there's obviously very specificities to sites, because the Dinaric Mountains are very karsty. There's a lot of percolation, so there it definitely made sense. Then it was expected to have a stronger response.
Anyone else have any questions? While I'm thinking, I have a quick question. You keep talking about site quality. Can you define what you mean by site quality? Because is this kind of like, because, you know, I just, because what you're talking about is very similar to when we were, the first time I was in the Pyrenees, and then we were working at, you know, kind of before the blue day, we're just looking at ring width, and we were always frustrated how poor the ring width of, I think it was mostly Pinus usinata that we were measuring, and how poor the response was to climate. But there was definitely a lot of evidence of herbivores in some of the sites at these tree line sites. And so when actually we went to do the site for that Reed and Wilson paper, I specifically went to pine trees that were kind of on the cliff edge where cows and such like probably couldn't get to very easily, to try to clean up the signal. I mean, is that what you mean by site quality? Is disturbance?
Yeah, I should rephrase. Yeah, it's not site quality. It would be physiographic attributes, right? So it would be pine. I mean, spruce is not going to grow on very, very much steeper, much drier, rockier, shallower soils, right? This is where pines comes, and this is essentially the sites where the pines were for the majority of sites, right? So they were on these shallower soils, rocky. So you know, just you would expect a much stronger dependence or much stronger variability in moisture, especially in the soil, simply because of that. So it wouldn't be site quality; it would be site attributes, right? So from slope to bedrock to just general site attributes.
Cool. Any questions from anyone else? If not, thank you, Krešimir. Great talk.
Thanks.
And I think for the rest of the people, I'll send an email around. There's a blue intensity discussion on historical datings, network development stuff next week. And then after that, we're still always open for people wanting to give online talks. So I'll try and get the committee to bully people. Or if anyone's got any ideas for me to finger, but there's lots of people doing stuff at the moment because of the special issue. So anyway, thank you very much again. And if no one else has any more questions, we might as well all go and clap. And well, for those who have the sun, enjoy the sun. And for those of us who have cold temperatures, we can actually go out and actually do some sport because it's nice and cool and not 36 degrees.
We'll try to send some nice weather your way.
This
15 degrees is nice enough as far as I'm concerned.
That's what I'm thinking as well. Be happy with what you have. It could be worse from what I've heard about Scotland and the islands.
That's definitely true.
Right.
Okay.
Okie doke, everyone. Brilliant. Thank you very much.
Cheers.
And I'll
Thank
put this video when
Bye-bye.
it's all down. I'll put it onto the YouTube channel at some point. So I'll send an email.
Cool.
Nice.
Sounds good.
Awesome. Thank you.
See you all. Thanks.
Bye, everybody.
Ciao.
Thanks.
Bye.
Thank you.
Bye.
Bye-bye.